A tank is full of water. Find the work required to pump the water out of the spout. And we're going to use the fact that water weighs 62.5 pounds per cubic foot. So here we have this tank here, this shape of tank. It's filled with water, and we want to find the amount of work required to pump all of the water out of this spout here. Okay, and so the idea is, and don't get bogged down with the physics here, trying to understand what work means and, oh, well, this is how a tank is shaped. Don't get bogged down with any of that. This is purely to illustrate the calculus, the integration process for a simple real life scenario. It's simple for the sake, because we don't understand the physics here. No one's an expert in this topic. And so it's just a simple case so we can apply physics to, so we can apply the integration process to something from physics or engineering, business, etc. And so, okay, the idea is that if we think about a plane that's at a single height value, okay, the idea is that it's going to take the same amount of work to move all of the water like in this plane at this height out of the tank, because the height is the same. It's all about the distance against the force of gravity that you're having to move the water. That's the work done in this case. So it's that perpendicular height, like the height against up and down, the height against the gravity direction to get to the spout. All right, but we can't think about a plane of water. To think about a certain amount of water, we think about a volume of water. That's what the density is based on, pounds of water per cubic foot. And so what we're going to do is we're going to think about a prism of water. And what we're going to do is we're going to, so we have this x here, x is 0 at the spout, and then going down, x increases to 6 at the bottom. We'll have these prisms, and each prism, we're going to break up this x-axis here into these equal width pieces to where the width of each piece is the height of a prism. And for each rectangular prism, we're going to assume that all of the water is at the same height. Like we're going to use the same height for each prism, the same height that all of that water needs to be moved up to get to the spout. So what we're going to do is we're going to break up this x-axis into pieces, these equal width pieces, where the width of each piece is the height of the rectangle, the rectangular prism. And the idea is we're going to assume that all of the water within each rectangular prism, we're going to assume one distance that all that water needs to be moved vertically to get to the spout. And so then what we'll do is we'll calculate the volume of each rectangle, then multiply that times the distance to the vertical distance, and we'll get a work done for to move the water out of that rectangle. We'll add up the work done for all of the rectangles to get the total work. All right. Now, what you can think about is if the delta x is too large, there's two errors that come into play here. First is that the amount of water will have errors if the delta x is too large. And to show that, I probably should have drawn it with here. It looks like I used the lower point as the function point, but you can imagine I could have drawn the rectangles in the opposite direction. I could have made the delta x down, so it would be kind of like that. And you can see, so if you do that, you're including water you're including extra water that's not there. If the delta x, like you see, and I think in one of the previous videos I mentioned that there was I think it was the position function, that there was no issue with a large interval size when it comes to the dependent variable. But what I said that I don't believe that was correct. I forget which video that was, but if your intervals are too large, then you're going to have the errors are going to be too big for both the dependent and the independent variable. So I forget where I said that, but and so yeah, I mean the weight of water is not the dependent variable. The work is, but I'm just talking about, so work is force times distance. I'm saying you're going to have error with respect to the force, the weight of water, and the distance. And I think in one of the previous videos, I said it like one of these wouldn't have error resulting from a large interval size, but I misstated that. So, okay, so yeah, if the delta x is too large, then you're going to get the weight of water wrong. I mean, if you use the midpoint, it wouldn't be so bad. But then also, if you imagine a large delta x, then I guess you would assume that all of that water is being moved vertically a distance of, and you'd have x, the midpoint of that interval, which isn't a bad assumption. But the problem with that is, if delta x is large, then you've actually got waters at different heights. So it's not going to work if delta x is large to assume that all of that water is being moved against the same height distance when you've got this large delta x, so you've got all these different heights of water. So you see, it's both the amount of water you're moving is going to have error, and the height distance that you're moving is going to have error if delta x is too large. Okay, but as delta x approaches 0, so as the number of pieces you break it up into, as the number of these rectangular prisms approaches infinity, what happens? Well, first of all, if we think about the distance the distance that each rectangular prism of water that needs to be moved to get to the spout is going to be just x, right? Based on how we have this set up. Well, we know whether or not you choose like the upper or lower point of the rectangular prism or the midpoint, we know with integration as n goes to infinity, it doesn't matter which one of those you choose. So that should be very obvious how the h distance, the height distance, is that error goes away as n approaches infinity. Okay, but then we also know from integration, from seeing like the area under the curve pictures, graphical pictures where the number of approximating blocks goes to infinity, like this idea of seeing like these gaps here, like seeing this gap here where you're including water that you shouldn't be including, those gaps go to 0. We see that in this area under the curves as the blocks, they put 50 blocks and like it's like hugging the curve almost perfectly. And so you imagine putting infinite blocks, and then it goes away. So as n goes to infinity, the error and the amount of water in each rectangular prism is going to be going to 0 as well. So that's how we can get a sense for, is this integration going to work? When you do the analysis like that, if the way you have it set up with your intervals and your approximating pieces, if as you think about as n goes to infinity, it would be clear, well, look, the errors aren't really going away for one or more of the variables as n goes to infinity, but here they clearly are. So to start, what we want to do is we want to calculate the value of the parameter we're looking for just like an ith rectangular prism. An ith meaning so any point along here. For any x value along here. So this would be like the I is equal to 1, then 2, then 3, for each block. This is the first block, the second block, the third block. For each rectangular prism, any ith rectangular prism, we want to calculate the work required to move that rectangular prism of water to the spout. Okay, so what is W of I? All right, well, we first need to get the weight of the water in that rectangular prism. So to do that, we need to get the cross-sectional area. And so to do that, we need to start by, so we know this dimension is 10 for any x, but what is this dimension? Okay, so we'll call this, let's say, y. Okay, so what is y as a function of x? That's what we're going to need. All right. When x is equal to 0, y is equal to 12. So we're going to start at 12, and then we're going to subtract. It's going to go when x is equal to 6, y is going to be equal to 0. So, and the slope is going to be, all right, so when x is equal to 6, y is equal to 0, and so x is equal to 6, and the 6 is canceled, you get 12, 12 minus 12 is 0, so it's going to be this, 12 divided by 6 is 2, so 12 minus 2x, so 2, okay, there's y as a function of x, okay. So now what is the work required to move like the ith block of water out to the up to the spout? All right, so the cross-sectional area, and you might be saying, well, Well, what do we use? Do we calculate cross-sectional area at the top or the bottom? Well, we're going to just write it like this. We're going to say, so the cross-sectional area is 10 times y. So 10 times y is 20 times 6, and we're going to say, we say this, xi star. That means we can choose any point we want, the upper part, any x we want within the interval, the upper part, the lower part, whatever. The middle, we can just choose. Okay, so that's the cross-sectional area, and then times the delta x, that's the volume, and then now that's going to be in cubic feet, now times 62.5. All right, and we've got the weight of water in that block, but we're calculating the work to move that water out to the spout, and so we need to multiply this by what? By xi star. And that is Wi. Okay? And so what we've got is 20 times 62.5. Okay, so 1250 xi star 6 minus there we go. So Wi, we can simplify this a little bit more. 1250 times 6, 7,500. Xi star minus okay, yeah, so there's Wi. And then like delta x would be b minus a divided by n, so 6 divided by n. We choose the number of rectangular prisms we want to use. That's what n is. Okay, and so the work done is approximately equal to, if we can do a sum here, sum from I is equal to 1 to n of this Wi, right? You can pick what you could choose. N is equal to 10, 20, and get an approximation for the work done to pump all this water out. But the work is exactly equal to the limit as n goes to infinity of the sum from I is equal to 1 to n of Wi. So I'll write this out. Right? So now this is what we want to evaluate. And what is this? This is an integral. So this limit as n goes to infinity of the summation, that's the elongated s. We're going from 0 to 6. Okay, now here's where the xi star, we can just eliminate the xi star, just write it as x, because as n goes to infinity, it doesn't matter which point you choose within the interval. So we can just put well, no, it would be okay, and then as n goes to infinity, delta x gets infinitesimally small. So we put, in place of the delta x, we put dx. And there we go. That's the integral that we need to evaluate. Okay, so we've got 7,500 divided by 2, 3,750. So 3,750 x squared minus 1250 divided by 3 is 416.7. Okay, and now we're evaluating this from 0 to 6. And we don't have to worry about 0 because 0, this is 0. So it's just this evaluated at 6. So 3750 times 36 minus 416.7. Well, what I'll do is this. Minus this times 6 cubed. $45,000. So 45,000 foot-pounds. That's the work. Required to pump all this water out of the tank.